different types of ultrasound. Most of you are probably familiar with ultrasound imaging because you may have gone to see a doctor, or maybe you have gone with your parents to see a younger sibling while still in the belly. But there is something called therapeutic ultrasound as well. And it does different things. At low intensities, you can do drug delivery. That was my dissertation topic. At high intensities, you can cook tumors, stop bleeding, or you can use ultrasound to change how much hormones are released from the glands. And that's the topic of this presentation. So it's ultrasound stimulation of beta cells in the pancreas to get more insulin to potentially treat type 2 diabetes. Why type 2 diabetes? Because it's a disease on the rise. So these statistics for the United States, it's almost 40 million people, or 11% of population are currently suffering from diabetes, and the numbers are on the rise because obesity is on the rise. And also, when I was young, type 2 diabetes was called like old people diabetes because you would eat not that well and not exercise that much, and then past 40 or 50, you may start having problems with too much sugar in your blood. That to be compared to type 1 diabetes, which is the one that pretty much you're born with, where your body thinks that your beta cells in the pancreas are actually a foreign body, attacks them, they die, and then you have to be on insulin from early age. Type 2 diabetes is a very slow disease. For many years, people may not even know that they have it, and it's characterized by systemic insulin resistance and then progressive insulin deficiency, which means initially beta cells work to have more insulin out, and they keep working, but too much sugar in the blood eventually kind of poisons them, and then they start dying off after some time. But this can take like 10, 20 years. So if somebody is diagnosed with type 2 diabetes, what happens is they typically, well, the doctor may tell them, okay, try to eat a little bit better, Mediterranean diet, whatnot, and then try to exercise, but also they typically put them on oral pills like medication, and they typically work well for about 7 to 10 years, but then they lose effectiveness and they have some side effects. Now, injections are also an option, and people typically get on injections a little bit later because that's, well, nobody likes needles too much. And for a while, the inhibitors were popular, but now agonists are the new class of drugs that are getting very popular because they have a side effect of weight loss. Now, if you talk to the patients, many of them feel like they would like to do something natural and not have a medication use. And that kind of was like a reason for us to think, is it possible to have an energy-based method to get the hormones out without using medication? Why did we decide to work on this? Well, I was like a long time ago, I was still a postdoc, like in 2004, I went to a conference in Kyoto, Japan, and there was just one abstract there by a group from Japan that showed that they're using therapeutic ultrasound to try to get leptin from fat, and then use leptin, which kind of makes you feel less hungry, to potentially treat obesity. Unfortunately, this group never continued with the work, never published the paper, but I found that super interesting. So when I met up with the biologist collaborator, Dr. Jeremic at GW, and he's expert in pancreas, I said, hey, let's work on seeing if therapeutic ultrasound may be able to get insulin out of the pancreas. Why would I think that this is possible? Because ultrasound was shown to have impact on neurons and causes different neuromodulation effects. So I knew that it's possible to potentially change the behavior of excitable cells to get something out. Now you can take a look a little bit here at where the pancreas is. Pancreas is pretty small, and most of it is an exocrine pancreas. What does that mean? That means that that's the pancreas that produces digestive juices to digest the food. but only 1% of the pancreas, endocrine pancreas, and it has endocrine function, which is insulin to lower the sugar levels in the blood, the glucagon to increase sugar levels in the blood, and there are some other hormones there that we're not going to discuss now too much. Now, if you look how insulin is released from a beta cell, glucose comes in and then starts the chain of events that results in the calcium coming in, and then that stimulates the exocytosis of the insulin coming out. Now, what we knew from neuromodulation studies is that therapeutic ultrasound at some low levels, these are about 10 times higher than ultrasound imaging and similar frequencies, can get calcium transients into the cell membranes. So we said, okay, if it's possible there, probably it's possible here as well. So that was kind of our general hypothesis that therapeutic ultrasound has been shown to induce calcium influx in various cell types, including fibroblasts, neurons, and chondrocytes, and then that maybe we can use the same method for our own application. There. So now a little bit on ultrasound. Ultrasound is
Dr. Starich, I think the slides aren't moving properly, so we still see the first slide, the title slide.
You're still seeing the first slide, and they have moved through many slides. Okay, so let's try again.
Let's try again, yeah.
Okay, so I'm so sorry. Okay, I'll open the slides fully because I went through many slides. Now let me try to share and then share screen. Now Erin, you still see the first slide?
Yes, now go ahead and click through. I think it will work. There we go.
Yep. Okay, so sorry for that. So,
okay.
So I said diabetes, trouble, type 1 and type 2 diabetes. I mentioned that. I mentioned the drugs that they use for treatment of diabetes. And then I showed this. You can still see slides moving, I hope.
Yes.
Yes. Okay, great. And then I was discussing the potential mechanism, and I'm going to stop here for a second. I said glucose comes in and starts a chain of events that results in calcium coming in and insulin getting released. And this is what we know from previous studies in neurons and chondrocytes. Now, if you take a look at this slide, ultrasound is a longitudinal wave that's above the sound waves that we hear. What do we hear? We hear between 20 hertz and 20 kilohertz. Our range of interest for therapeutic ultrasound application for hormonal release is between 400 kilohertz and 1 megahertz. And while ultrasound imaging is between 1 megahertz and let's say 15 megahertz at 0.1 watts per centimeter square, our intensities are, let's say, 1 watts per centimeter square. This does not cause damage in the body much, but can cause some minor changes in the bodies and has been used for decades as physiotherapy. What is that? When somebody has a sore muscle or a broken bone that needs to be healed better, similar ultrasound is applied on that to kind of heal the injury and improve the outcomes without causing any adverse effects in the tissues. Now, ultrasound bioeffects can typically be separated into thermal and mechanical. Thermal, as I said, can be used for tumor treatment at low thermal levels, also at high thermal levels, at special types of drug delivery, but also you have mechanical effects. In mechanical effects, there are bubbles that are formed in the tissues or solution next to the tissues that you can manipulate to break them, to cause like pits in the membranes or changes in the membranes that are temporarily, and then you can have some effects like drug coming into the cell or some other stuff changing in the cell membrane. You can also use ultrasound just to push stuff, and that's useful for drug delivery. You can, let's say, deliver more of the drugs into the eyes or into the skin, for example, for transdermal drug delivery. So these are some examples of thermal effects. As I said, when I was a postdoc, I worked a lot with high intensity focused ultrasound And for example, one of the projects was to stop bleeding in the abdominal injuries, like a liver injury in astronauts. At that time, I mean, NASA was paying me as one of the postdocs to figure out how to use ultrasound imaging with ultrasound therapy to stop the bleeding and save the life of an astronaut. They had like a mission to Mars at the time, 2020. It didn't happen now, it's like 2035, but they were working pretty seriously on finding ways to treat serious injuries in astronauts without sending surgeons with them necessarily. Mechanical effects, there are many out there. What's popular these days is opening of blood-brain barrier, for example, and delivering more of the drugs into the brain for treatment of brain cancers, for example. But regarding our own hypothesis is that low-intensity therapeutic ultrasound can present a selectively targeted and non-invasive treatment for earlier stages of type 2 diabetes. Why earlier? Because in very late stages, the beta cells will die off and then we cannot stimulate them. But there is still a couple of decades in the earlier stages of the disease of the patients that our work can be useful. So when you do this type of studies, you first test in vitro in a cell setup, and that's what we did. And then the next step is to treat ex vivo in like whole pancreas. The next step would be to work in vivo, but not in humans, in, let's say, the rat or mouse model. And then the last step is to do some preliminary studies. Well, the pre-step is to do some modeling to see whether it would be safe to work on humans, and then do a very small pilot studies in humans. We have done modeling studies. We have not made it to the human studies yet, but now we are working with a physician from Children's National Hospital who does use focused ultrasound for treatment of brain tumors and bone tumors, and he's interested in working with us on trying to treat the pancreas as well. So what you see here, actually, I forgot to say, is an ultrasound transducer in the water because ultrasound would not travel through the air. And we put the beta cell solution in this cuvette, and we are applying ultrasound and seeing how much of insulin do we get out. That's ultrasound treatment. And there is sham treatment where you are pretending that you are turning ultrasound on and you don't, and then you compare the two treatments. What we wanted to do first is to test whether ultrasound is safe not to kill the beta cells while we are trying to stimulate them. So we tried different frequencies, 400, 600, 800 kilohertz, 1 megahertz. At the lower frequencies, there is more of mechanical effects which can rupture the cell membranes more seriously and kill the cells. And you can see that the cells did not survive very well at the lower levels. At the lower levels. But then when of frequency, but at higher frequency, they were surviving pretty well. And then now we focused on just working at the right frequency ranges, and then you test sham, you test positive control with glucose, and then you see how much you get out with ultrasound application, how much insulin you get out. This is extracellular insulin. Now, a question may be raised, okay, maybe you just killed a couple of cells, but you released all of their insulin. So you have to take a look that there is actually reduction in intracellular insulin content at the same time. And we did see that with statistical significance. Now, we were curious to really study the calcium transience mechanisms as well. What you can do is have electrodes, put the beta cells in the Petri dish, and then see how much of a compound you can get out of the insulin-containing vesicles. Unfortunately, insulin is a non-charged particle, so we had to put the dopamine, which would mimic insulin, in these vesicles and then see how well we can get them out. And we were applying similar frequencies, as I mentioned before, 800 kilohertz, and then intensities that are pretty low, 0.1, 0.5, and 1 watts per centimeter square. And what you can see is if you apply ultrasound, you get the compounds out if the intensities are right. And then, these are the different intensities. If it's too low of intensities, you will not get any outcome. And the other thing we could do is to put So we can do is put a calcium chelator, which is something that blocks the calcium such it cannot travel, and see if it's indeed the calcium mechanism in play. And if you see EGTA is a blocker of calcium, and you can see that we have much less of effects. It's the green line if calcium is blocked. So it's not just that that's the only effect, the calcium transients, but it looks like that it's a dominant effect. So, and then if you can see, ELISA test can be used to measure the insulin levels in the solution. And when you use ELISA test, you can see that EGTA will block the calcium levels and the insulin release. Now, this previous work was done by he was our bachelor student and master student, then he stayed for a PhD. So my former student, Ivan Soares, and then he left to become, eventually now he's a research scientist at INSERM in France, which is basically an NIH of France. And a new student took over this project, Andrew Tran, shown here, and he wanted to work with the whole pancreases. And what you can do here is slice them and image them and see what's metabolically active when you apply ultrasound. He was looking at both exocrine and endocrine pancreas. This was not easy to work out because pancreas is a very sensitive tissue. It breaks easily. So he spent a lot of time working on how to embed the pancreas of a rodent into the gel freshly after the sacrifice of the animal and keep it sturdy enough such that you have a nice little slice for imaging. So this is how it looks like. It's slicing of the pancreas. And then eventually he worked out how to have these nice flat slices, put it under fluorescent microscopy and see what kind of changes he's getting at different levels of fluorescence. And what he concluded is that ultrasound may be stimulating the exocrine pancreas, but there is the most pronounced effect on the endocrine pancreas. Now, if you want to do this type of studies, you have to do some image processing as well, because ultrasound is pushing the tissues. So what Andrew had to do is figure out how to track the islets. What you see here is an islet, and he found a way how to track the islets such that he can follow them properly, such he knows what's going on in his images. And the overall result is that therapeutic ultrasound may have a stimulatory metabolic effect on the pancreatic islets, which is similar to glucose. Now, another student, so now Andrew Tran graduated and he's now a postdoc at University of Pennsylvania, and John Hill became a PhD student in my lab, shown here. His background is actually not engineering. He came from nutrition and exercise sciences at Virginia Tech. And he did gene expression for his undergraduate studies, and he was very interested in seeing maybe we are causing some changes with ultrasound to the pancreas, to the endocrine pancreas at the cell level, right? So what he did is he applied the ultrasound parameters we used before, but now he was focusing on testing of genes. The genes that he tested were insulin, that's the one we are working on, glucagon, that's directly opposed to insulin, amylin, that has like a synergetic effect with insulin. And then the binding immunoglobulin protein, BIP, is the one that you can like test to see if the cell is in stress. Now, here we moved up a little bit closer to the translation into human practice, how we were getting human donor islet cells. So this is now work on human islets. When somebody passes and had signed to be a donor, there is a company that works actually with the NIH to supply the labs with the human islet cell, human islet islets that people, the researchers, can then work on and study, mostly diabetes, right, and other endocrine diseases. So we had 9 overall donor samples, and this is certainly similar, but now he has to do other type of analysis that's suitable for gene expression. what he learned is actually that there is no impact really at the gene expression level in our studies. So he did detailed studies and saw that there is no statistical significance there. So his outcome was that ultrasound mechanisms, other ultrasound mechanisms may be responsible for this work. Now, this is all great, but the most important thing is to do in vivo studies. So Tanya Singh, she was in my lab actually throughout her bachelor studies, and then she stayed for a 1 year, a 5-year master program, and now she's a PhD student at UCSF and Berkeley, and soon to be done, I think next year. I just saw her at the conference. She's going to be done next year. So she was brave enough to actually breed the mice with diabetes. That means she had 1 male, 2 females. She bred them into a colony. And then when after several months they developed diabetes, she tested in them therapeutic ultrasound to see whether it's safe, effective for in vivo application. And this is the mouse. The parameters are the same as we used before. For in vitro studies, these are our mouse groups. And what you can see here is you take blood from the mouse before the application. You don't cut anything, you just snare. I mean, you remove the hair from the belly, you apply ultrasound, and then you take immediately after ultrasound application for 5 minutes, you get the blood out, you test how much insulin is in the blood. You test again and see how much insulin is after 35 minutes, because there is like a dual release of insulin. Immediately some is released, and then some is released later. In the normal, it's a biphasic release if the insulin would to be released via glucose. So we did the same type of application. We didn't see any, we survived some of these mice. We didn't see any gross damage inside the belly after sacrifice. We didn't see any damage on the skin. The mice did fine, and there was insulin increase in the blood with statistical significance after 5 minutes of application. For glucose, it was harder to see any changes because first anesthesia impacts the glucose level, and the other thing is we were not allowed to starve the mice before the application of ultrasound. So some ate more, some ate less. So we only know that the insulin was indeed released, but we didn't see statistically significant reduction in the glucose levels here. And the last thing I'm going to talk about for the last, we have another 6 minutes, is can you apply this in humans? So Tanya and an undergraduate, George Saab, decided to model human patients, and we had a grant with Children's National, so these were adolescent human patients. So we got CTs of the pancreas, of the whole abdomen, of 2 normal size adolescents, like teenagers, and then 2 obese teenagers. And then we were trying to figure out where to put an ultrasound device to have a safe treatment. And if you see here, what we see is the envisioned eventual application is an ultrasound transducer over the pancreas with the driving system, and then the blood glucose monitor is with the embedded glucose measurement. And if you see that the glucose is going up, ultrasound can be applied after the meal, let's say 3 times a day. Yeah, we discussed this. We actually, VW is one of the hubs for NSF I-Core program. That's a small business startup programs for students to learn how to do like business and startups. So we did that. I and my students did that and talked to a lot of patients, a lot of clinicians, and then FDA and NIH. And it's, I mean, FDA is a little bit concerned if the patients are in charge of the treatment, but I mean, it's not impossible. What they were saying is maybe you want to implant the ultrasound transducer instead of having it on the surface. So there is less responsibility on the patient. So there are modeling softwares out there that can model biological tissues and ultrasound application to biological tissues. And one of them is OnScale, which is what we use. These are the cross sections of the actual human patients that we then modeled, as you see. And you can see the pancreas here. And then we were trying different locations of the ultrasound to see whether we can get enough of intensities in the pancreas without causing any damage. Potential damages to the skin or to the intestines and the stomach, because there is air bubbles there that can cause interface. So we saw that we can get sufficiently low temperature increases and sufficiently high intensities if the patient abdomen is applied. Now, a little bit higher intensities because this has to travel through layers of tissues. It's not like a cell solution in the water bath. So you have to increase the intensities a little bit. So now what we are getting ready to work on, there is the newest student is Bridget Thorpe, and what she needs to work out, and I mean, we are about to start that hopefully in January, is you can buy diabetic rats, Zucker diabetic fatty rats. And what they do is you bring them to your lab and you feed them basically a special diet, which is kind of unhealthy diet, a lot of sugar, a lot of fat, and then they develop diabetes after 12 weeks. And then we're going to do a more formal study with survival to see what is the outcome in diabetic rodents. And the other thing we are currently working on is with Dr. Karun Sharma that I mentioned from Children's National. I have a student there again who is doing retrospective and prospective studies of images of the pancreas in adults now with ultrasound and MRI to finalize the treatment planning for the human application. So he's working on IRB protocol now to hopefully do the prospective study, and he's already allowed to do a retrospective study. And this work was funded by NIH. First, we got like a small grant that's an RO3. Then we got a large, like $2 million grant that's an RO1. And in the meantime, Children's National has a large grant through NIH, and then they give small grants to different pilot programs. And we had one of that smaller grants to do the modeling of human of the potential human treatment later. And that's my presentation. I think I'm right within the time, and I'm going to stop sharing now. And sorry again for not moving the slides, the first 5. I was moving them very nicely on my own computer, but that didn't work, right?
No worries. Thank you so much, Professor Vesna. I think that was super interesting, super informative as well. Just a quick reminder for students. I can see Pranita's question that has come in the chat box. I would recommend that you have all the questions in the Q&A tab. That will be super helpful for us to keep a track of any kind of questions that come for Professor Vesna. But before we move on to learning a little more about the George Washington School of Engineering and Applied Sciences, I have a quick poll question that I would just like to know a little bit about from some of you folks. So I'm just going to quickly launch this poll question. Just give me a second. Yeah. I think you can see it right on your screen right now. How likely are you to pursue a STEM master's in the US over the next 2 years? So either in upcoming fall of 2024, or if not fall, if you are slightly early in your process, how likely are you to do that? Maybe in fall 25. I think that's the question here. So if you can click on the poll tab on your mobile devices or on your laptop, wherever you are joining us from, at this session from, that will be super helpful. We have close to 230 people in this Zoom meeting right now. We want a few more people to answer. Just a reminder, click on the poll button on your mobile devices, your laptop, and you'll see how likely are you to pursue a STEM master's in the US over the next 2 years. Highly likely, somewhat likely, or you want some more help or some more information to help you take your decision. I'm going to wait for just a few more seconds before I close this poll. We already have 60 responses. So thank you so much for 60 of you. I'm going to just end this poll right now. And for everyone to see on your screens, for Erin and Professor Vesna, more than half the people that have voted are highly likely to pursue their STEM masters in the US over the next 2 years. So thank you so much for half of you that have done that. 12%, some of them are somewhat likely, so they're still thinking about it. And 35% is what Erin has in front of her to convince as to why a STEM master's program in the US would be a very, very good decision for them as well. So, once again, less of me, more of the speakers that are going to be here today. And just to quickly introduce Erin, Erin has been the Senior Associate Director of Recruitment and Guidance at the George Washington School of Engineering and Applied Science. And she's going to be taking us through a little bit about GW, the application requirements, eligibility criteria, and stuff like that. One quick reminder, if you have any questions about GW or for Erin, use the Q&A tab and get your questions upvoted so that we'll ask the most upvoted questions in the Q&A section that we will have right after Erin's presentation. So thank you so much for everyone we are 220 people plus still here, and over to you, Erin.
Thank you so much. Let's see if I can, how's the screen sharing? Is it good?
Yep, for now, if you could change your slide. Yep, that looks good. Yep.
Okay, great. Okay, well, thank you so much for that introduction. I'm very happy to be here today. I host numerous events with the Scie team throughout the year, and we really appreciate all the students joining us, prospective students joining us for these events. So I'm here to talk to you a little bit about GW engineering, but as a person who's in a counselor role, it's my job to help students understand if GW engineering is a great fit for you. I'm happy to answer any questions that you have about our programs and pursuing your future degree at our university. And I can also answer questions about just studying in the US in general. So a little bit about GW. We have 14 schools and colleges across the university, over 2,500 full-time faculty, and over 25,000 students. One thing that makes GW unique is that more than 15,000 of our students are graduate students, which is more than our undergraduate student population. So that really speaks to a strong emphasis that we have on our graduate level programs, providing opportunities for students, providing resources for students that are in that phase of their academic life and their career. Here at the School of Engineering and Applied Science, we have 6 academic departments, of course, biomedical engineering being one of them, 11 fields of study. I'll show you a little bit more about that in a minute. More than 90 plus faculty members, tenure and tenure track faculty members, and 22 million was the last count, I believe, this past year in research spending. So again, that number is so significant because it really trickles down to opportunities for our students, especially our graduate level students, as they're interested in research opportunities, in utilizing new technologies, in working with new faculty members on cutting edge projects. And this here is our Science and Engineering Hall. So this is one of the largest teaching facilities in Washington, D.C. It's a very large building. It's the hub of a lot of what's going on for our programs and our students. Our faculty offices are in this building, our department offices, my office, our student advising services, career services, and then a lot of the technologies and research labs that our students may be involved with at some point in their academic time with us. So a little bit more about our areas of study. I'm just going to briefly show our MS programs and our PhD programs that are available to students. Of course, within the programs, there are different areas of focus, and we do really pride ourselves on offering interdisciplinary opportunities to our students. So a lot of our programs, students are able to take a few courses in other areas of study, other fields of study. There may be classes offered in conjunction with things like a medical school or a public school of public health, where you can really get an interdisciplinary look at the field that you're studying. So these are the MS programs up on the screen, and then here we have our PhD programs offered in many of the same areas. Of course, you would be specializing under these main subject areas in a lot more niche areas of research and development. And then a common question that we get from students who are interested in pursuing a degree program in the US or at GW is, what about scholarships or funding opportunities? So for the master's level here at GW, we offer scholarships that could range from 25 to 75% of our tuition cost. These are based on merit. So they're based on your academic background and history, also on your experiences, on organizations that you're involved with, conferences you've attended, research that you've done. There are a lot of different factors that we take into consideration when we make these funding decisions. And then for students applying for PhD opportunities, although it's not guaranteed, a lot of the students who are admitted to PhD programs are also provided a funding package as well, which is considered full funding for the students. So that would be considered tuition coverage for your program, as well as a living stipend for your time in DC. Our W. Scott Amy Career Services Center. So career services is a big factor that I like to talk to students about when they're thinking about pursuing a degree in the US, because you're really investing in the academics of that degree program, but as well in all of the support services that a university will provide you. So it's really important to look into those services and gain a good understanding of how this university is going to help you achieve your ultimate professional outcomes. So we're very lucky that we have a career services center inside our engineering school. So it's separate from the main GW Career Services Center, and it's dedicated exclusively to working with our engineering and computer science students. Since I know most all of the students on the call today would be international students in the US, it's important to note that our career services advisors are very experienced with working with international students. We can help you job search not only in Washington, DC, not only in the US, but around the world, as well as help you find opportunities for things like CPT and OPT, which a lot of our international students are hoping to take advantage of. So our advisors have a lot of experience working with students on these things and can really help you navigate that process from the time that you arrive in the US. So as you're thinking about your career goals, your academic goals, the universities that you're interested in, and particularly about GW Engineering, hopefully, a little bit about what is our advantage as an institution. We really pride ourselves on having highly specialized academic departments. So we have a lot of really interesting and unique, highly qualified faculty members who are doing cutting edge research that trickles down into your coursework as a student, the opportunities that are presented to you for events, for research, and so forth. We have small to medium class sizes, so students really can get the individual attention that helps them ensure that they have a good learning experience and that they're getting to explore the knowledge that they're interested in their subject area and gain those connections with faculty members, of course. And then we have a lot of longstanding connections with for research projects, for internships for students, for job opportunities. The institutions named on the screen here are just a few of the organizations that our students have done research with or gone on to be employed by after their program. But we're fortunate that we graduate a lot of very talented students in engineering and computer science, and a lot of the employers that they go on to come back to us over and over again looking for more highly qualified candidates to fill their positions. So that is definitely an advantage of our institution. If you have some questions, I'm going to wrap up in just a minute, and I know there have already been a number of good questions for Dr. Zverich, but if there's anything about admissions, about studying in the US, I'm happy to answer that as well. If you have questions specifically about attending our school, our graduate programs, we encourage you to reach out to our current students. They're available on our website. These are just 4 of our graduate ambassadors. I think there's 7 in total, but just showing you 4 as an example of students that you can reach out and chat with and ask questions about life in our programs, life on our campus, what's it like to study at GW and in Washington, DC. Ellie, for example, is a current student in our biomedical engineering department, and is very happy to chat with you about questions that you might have about studying in that department and the coursework and that sort of thing. So we encourage you to take advantage of that opportunity as well. I'm going to wrap up here with my formal presentation and turn it back to our hosts for questions. But I would like to offer anyone who attended the session with us today an application fee waiver. So for spending that time with us today, if you do decide to apply to GW Engineering, at the end of the application, you're welcome to enter this code SEED NOV for November and OV 23. And that will waive your application fee for applying to one of our upcoming MS or PhD programs. Our website is on the screen. My email address is on the screen. Myself and a few of my colleagues are in this email every day, answering questions from students and helping point you in the right direction for any information that you need. So thank you so much for joining us today, and I'll turn it back over to our hosts, and happy to take any questions.
Great. Thank you so much. Thank you, Erin, for your wonderful presentation about GW. Obviously, there's a lot for us about this. Just for the 190 of you that are here and are interested in studying at the George Washington School of Engineering, there are so many benefits that you have already received by attending this absolutely free masterclass that was hosted by GW with Erin and Professor Vesna. One is you have an application fee waiver. So if you're applying to GW, you will save on a few dollars, a few hundreds of dollars rather, on the application fee, and that gets completely waived off. You have to just use the code SEED NOV23, and I've put that in the chat box. Also, there have been some questions about scholarships, about the specific GW scholarships. I'm going to let Erin answer that. But for everyone who is interested in applying to GW, there are some exclusive scholarships that you are already eligible for because you have been an attendee of this masterclass, which is the SEED and the GW scholarship, where there are if I'm not wrong, if I remember correctly, there are 4 awards that are there on offer. One award is for 75% of the tuition fee. Yes, 75% of the tuition fee can get waived off, and 2 awards where there are 50% of the tuition fee can get waived off through the scholarship process, and the last one is 25%. So 4 exclusive scholarships only for candidates who have attended this masterclass and other masterclasses hosted by the George Washington School of Sciences. So I would recommend that you click on the link and just express your interest, and we'll reach out to you with what the next steps would be to get hold of that scholarship. 75%, 50%, and 25% scholarships on offer exclusively for attendees of the SEED Masterclass. Moving on to some of the questions here. I'm going to ask, we have a range of questions, one about the masterclass itself and some questions about GW. Since we're talking a little bit about scholarships, the most upvoted questions, obviously, Erin, has been around scholarships. Sanika, Mukaddas and Hasnath have asked questions about some of the special scholarships that are available, not only for the biomedical engineering course, but also for some of the other courses that are on offer for MS programs.
Okay, yes. So for MS students, like I mentioned previously, we do have tuition scholarships for our students that range from 25% to 75%. Of course, that's on a scale of sort of competitiveness of the applicants. So our 75% scholarships are awarded to our most competitive applicants, again, looking across all of the different factors in your application. So we're looking across your academic history, but as well as any test scores, your recommendations, your resume for any work experience and that sort of thing. And the scholarships go down to 50% and 25% of tuition cost. There's nothing that you need to do with us separately to apply for these scholarships. So all of the students who complete an MS application will be considered automatically for these funding opportunities. And if you are awarded a scholarship, it will be noted in your admission letter. So you'll get that information at the same time to consider your decision. You'll be notified that you're admitted to the program and that a scholarship was available to you. Does that help?
Yep, absolutely. Thank you so much, Erin.
Okay.
My next question to you, Professor Vesna, you've been in, like the department chair for the biomedical engineering. There are a lot of questions coming from students. Nandini has asked, and Sharish Liaquat has also asked about some of the backgrounds of students that come into the biomedical engineering program as such. What kind of backgrounds are eligible if there is a strict policy? If not, if it's open. Shashri's mentioned that he is from a pharmacology or a medical background. There are some other folks, yeah, in the Q&A tab also mentioned about they are from chemical engineering and pharmacy. Would you like to throw some light about the backgrounds of students getting into the MS in biomedical engineering, please? Sorry, Doctor.
Sorry, I forgot to. So I'll start again. So as of several years ago, we changed our admissions requirement to be more flexible regarding non-traditional backgrounds. For us, that means non-engineering background. If you're from any type of engineering, you will have enough of math and physics to get in, and that's not the question. If you're coming from biotechnology or chemistry, biology, different type of schools, right? They will all be considered, and I'm actually the person that reviews then the transcripts, right? If you're coming from engineering background, you will be reviewed at the school level in our admissions office. If you're coming from an unusual background, you will end up with me, and I have done this for a long time for EC department as well. I will look how much math and physics you have. So, and specifically, I will look whether you have 2 math classes and 2 physics classes, ideally with some type of lab. So, from Indian students, I think a lot of them with non-traditional backgrounds can still get in, based on my memory on review of this type of backgrounds. If you are a student from the United States, you typically have enough of math and physics, even if you're coming from biology and chemistry. So in general, it depends. But if you are missing some physics classes, you might want to add some physics, and that would allow you to get into an engineering program. Now, the question was brought up over scholarships. I think Erin was discussing the tuition discounts, and that's a benefit. But regarding the paid positions, right, as a teaching assistant or a research assistant, generally, it's PhD students get a full support, and they take away all of our positions. So generally, our master students get a tuition benefit, but they have to pay for their living expenses on their own and prove that they have enough of living expenses. That said, I mean, we had a good number of students that start as a master student, and if they perform well, they start working in some lab, maybe they do a thesis, we take them as our PhD students afterwards. So, I mean, that had been kind of a more popular path in the last like 4 or 5 years. Why? I mean, because our NIH grants come not necessarily when admission times come, and suddenly you have the money and you don't have a student, and then you start looking at the students right? And I mean, they sometimes switch people directly from master's to PhD. Sometimes they graduate and go. So, but that's current situation to be like for students to think about, right? If they come as master students, they are generally self-supported, but they may have some benefits in tuition. Now, I see some science questions here, only a couple. I mean, is this a good time to answer them and then continue with admissions?
Absolutely. Maybe you want to answer some questions regarding,
there are only a couple. So, I mean, the question from Zanib was, why is type 2 diabetes curable? I mean, it is curable in a couple of people. It caught early, and a person is younger, and they change their life completely. They start exercising, they lost like 50 pounds. I mean, I heard of type 2 diabetes being curable. For majority of people, it's manageable. You want to keep yourself healthy by a very good management of your glucose levels, such that all the horrific like side effects of type 2 diabetes in later years don't hit you, and that's blindness and kidney failure and amputations and heart failure. I mean, it gets really bad, but if somebody maintains their diabetes well, they never make it to that point, and they live their whole life managing their disease. So now what are we adding here is another way to manage the disease. In the end, it may happen that it's just going to be a combination of ultrasound and pharmaceuticals in the end, and not just ultrasound. Now, other side effects of ultrasound, so far we only worked in animals and we did not see any adverse side effects. Some things that we should be aware is that if you let's say get too much insulin out in a human, you can kill hypoglycemia can kill a person, right? So I mean, this should be taken very carefully to not have too much insulin in the blood, and like the control of the whole process has to be very careful. Another thing we're going to pay attention to is pancreatitis. I mean, maybe we want to get insulin out, and somehow pancreas doesn't like ultrasound applications. So that's why we have to tread very carefully when moving into human. And that's the pancreas is a very sensitive organ, and it's also very necessary. So I mean, we have to be careful. Now the last question was, would biotechnology, this is not the, okay. No, I think this was all of the ultrasound questions that I can see. The rest of the questions I answered. Biotechnology as a background has passed in the past if there was enough math and physics in the background. Right?
Wonderful, great. Thanks so much. I think there's one more question I'd like to ask Erin. Some of the students here have asked, especially in the chat, is they're slightly confused on what kind of master's programs they should focus on. What is your recommendation, to students? Should they go into the master's program that is super duper specialized into one particular field, or a slightly generic master's program where they can pick and choose what kind of industries or what kind of career prospects they have? So one question to you about how can a student pick, and my final question to you, Professor Vesna, is if you can also answer a little bit about the career opportunities after someone completes the biomedical engineering program. But I'll let Erin go first, please.
Okay, sure. So, gosh, great questions about pursuing the master's and how to sort of select the best program for you. So, I will say at our university, our degrees are MS degrees, typically Master of Science, but you can choose whether or not you wish to pursue a thesis. So that is one factor that you would look into at our program and at any other programs that you're interested in, is whether or not a thesis is part of the program. For some students, they want that. They really want some more in-depth research opportunity. They might be thinking about going on to a PhD in the future, and they really want to get started with honing those research skills. So a thesis would be a great option for them. For other students, they're interested in more going directly into industry, and they want to do their master's by coursework, and that's certainly an option for us as well. So that's how it works at our university, but other universities might have different requirements for the different degree requirements. In terms of how specialized to get in your master's, it really depends on your professional goals. So again, whether or not you're going to go right into industry, whether you want to be research focused, whether you want to work in a tech company, whether you want to work in medical instruments or devices, whether you want to go on to a PhD and work in academia. There's so many different paths that you could take with these master's programs. I will just emphasize that, when I talk to students, I try to emphasize that a master's is a specialized degree. So even though you might be coming from a different background, it might not be specifically biomedical engineering. The reason that you're joining this degree program is not just to get some general information about biomedical engineering, but it's to become a master of this subject area. So I think you do want to have at least a little bit of specialization as you go through your degree program, so that when you go to look for your career opportunities and find a job in the field, you can really clearly articulate why you stand out. What have you specialized in? What are you really good at? That's the advice that I give to students. I'll turn it over to Dr. Hizdarich to talk a little bit more about her question.
So I just want to comment that actually our Master's of Science degree is fairly flexible, because unlike many other programs, we allow 5 of our graduate classes to be taken in other departments. So that means that some people want to learn more about public health and policy, and they can take multiple classes there. Some want to learn more like computer programming, and they can go to computer science and take some classes. Further, we allow 2 of the classes to be undergraduate classes to kind of fill up the holes in the background. So they can be 3,000, 4,000 level classes. So there is a lot of flexibility there. People can focus on, take medical device classes within BME, but then take some of ECE general device classes on nanofabrication, right? So, I mean, there are different options, or they take classes in medical school if that's something that they're more interested in, like clinical medicine. That's one comment. The other one is master thesis is getting more popular. Like, it's not required. I mean, if you want to go to industry afterwards, I mean, maybe it's not the most important thing, but still allows you to not take two classes, that's 6 credits, and you work in somebody's lab for 2 semesters, 3 semesters. You can take like a research class in addition to master thesis classes. You kind of get to learn about academia better and become an expert in a specific topic. For PhD students, we require that they publish to be able to graduate. For master's students, no. But I mean, we strongly encourage that they have a first author publication based on their master's work, and we are all working towards it because it's beneficial for everybody. So getting a paper out may distinguish you from other candidates. I don't think it's the super easy at the master level now to find jobs because there are a lot of master students. It's not impossible. I think Aaron can comment on this, but I mean, majority of our students are gainfully employed very soon after graduation, right? They may be worried like the last semester, but they have not heard of anybody that's like sitting unemployed in the field, right? Some end up like working in medical school as research scientists. Some go directly to industry. There are all kinds of outcomes. I mean, for non-US students, government is a little difficult, but not impossible. I had like an Indian student before that did his master thesis at FDA. And so for master thesis, you don't just need to work with like 9, 10 of us that the faculty in BME department. You can go and work at FDA, at NIH, at Children's, at NIST, wherever, and have advisor there, have a co-advisor in BME department. And I mean, for Dushyant, this was a way in. So although they do not like doing visas for foreigners at FDA, I mean, he was already there, he was doing the thesis, then he got some internship. So, I mean, he got employed there and eventually went to work for an ultrasound device company in California. I think he's still there, last I heard, right? So, I mean, in the end, if you end up with us, it's good to talk to your faculty advisor early on what your desires are, so we can help you choose the classes and also what's the best option for you. But it's really varies on the person. Were there any other questions that I missed or what I needed to respond?
No, I think we've covered most of the questions, and we're slightly over time as well. A couple of questions have come in about the application fee waivers and scholarships, which has already been mentioned previously. So there's a recording that is there on YouTube about the session for the folks that might have come in a little late, Muhammad and Blessing. So I'd recommend that you have a look at the recording and get some of your answers as well. I think we've gone a few minutes over time, but this is highly appreciated. We have almost 100 people in this room still here, so I think that shows the level of interest of folks in the field of biomedical engineering and about studying in the US, specifically at the George Washington School of Engineering and Applied Sciences. I want to take this opportunity to quickly thank Erin to make time for the session, and also, and more importantly, to Professor Vesna, who's taken out time from her busy schedule in order to share her thoughts about this very interesting topic and a lot about GW School of Engineering too. Thank you so much once again for your time. Thank you so much to the hundreds of you that are still here and who've patiently waited, asked questions, and been a part of this wonderful session. If you have any questions, feel free to reach us. You know where to find us. The session is also available on YouTube for the folks that have missed it. If you have any friend that might not have registered, etc., wants to still study at GW, you can send them the YouTube link. Each of you will get a YouTube link tomorrow on your WhatsApp on the registered mobile number. So you'll be able to access it and it will be with you at a click of a button. Thank you so much to everyone who's joined this session, and have a nice rest of the evening or the day wherever you're joining us from. And once again, thank you, Erin and Professor Vesna, for your time.
Oh, thank you very much. And I just wanted to say, feel free to email me if you have any questions. So I'm the only person with this name. If you type in my name, my email will show up and you can follow up if you want. Okay, thank you.